Hello students, in this video we'll begin our discussion of functions of a complex variable. So let omega be, it doesn't have to be an open subset, but that's going to be our typical context, be an open subset of the complex plane. And let f be a mapping from omega into C be a function this function is going to be a complex valued function. It's going to output complex numbers. Remember that what's a function? A function is a codomain, a domain, and a rule which for every element in the codomain there's exactly one element in the domain, right? So in other words, for every element, there cannot be two elements in the codomain for one element in the domain, right? So that's what a function means. And so we call these complex valued functions. This is a complex valued function. Okay? And so what's the idea? So the idea is if I give you a point, so if z is x plus I, y is in the set omega, so if I give you a point in omega, then f of xy, f of z, which is f of x plus iy, is going to be equal to what? Is going to be equal to some function. It's going to be something that is only real, because this is going to be a complex number. So this thing over here is a complex number. So this is a complex number. That's a complex number. In complex numbers, I can write this as the real part. This is the real part of f of x plus iy plus I, the imaginary part of f of x plus iy. Okay? Because any complex number is the real part plus I, the imaginary part of itself. And traditionally in the state of complex variables, you don't want to have to keep writing this clumsy bit around all the time. So you're going to write this as u of x, y, which is, of course, the real part, plus I v x, y, which, of course, is just going to be the imaginary part. So in order to avoid using this clunky notation for complex value functions by using these functions u and v. Excellent. So let me show you an example of this. So for example, I'm going to look at, here's an example of a complex valued function. I'm going to look at f of z, which is going to be z squared plus 2z bar. Okay? So I'm inputting this, of course, it takes any complex valued function, takes any complex z and gives me another complex number, right? So in particular, what would this say? This says, if I look at f of x plus iy, this would be equal to what? This would be x plus iy squared plus twice x minus iy, okay? And of course, x plus iy squared is going to be x squared minus y squared plus 2ixy. That's a good exercise for you all to do to practice your complex variables, plus 2x minus 2iy. And so if we gather the real imaginary terms, is going to be x squared minus y squared minus 2y. Plus, whoops, excuse me, that's not quite right. I'm not good at factoring. Let's figure that out. X squared minus y squared, and then plus 2x. Great. And then I times what? And then I times 2xy, and then minus 2y over there. Beautiful. In other words, this over here is going to be my what? That's going to be my u, and that's going to be my v. Easy enough, okay? So that's a complex valued function, okay? Now, of course, we're going to start to study elementary complex functions. Now, what do I mean by that? I mean, elementary complex functions are the functions from calculus. E to the z, sine of z, cosine of z, sinh z, cosh z, tank z, tangent of z, log z, Bessel function j0 of z. All the functions we know from calculus, inverse sine of z. These functions, I can look at z minus 1 over z plus 1. All the functions we know from calculus, so I can plug in a complex variable to them and get some information about what u and v are. So that's going to be a large part of our complex variables course, is understanding the elementary complex functions and properties of the elementary complex functions. Okay, that's just an example of complex function. Now, of course, I want to tie in this idea of complex functions to what? To the standard things like continuity, differentiability, and integrability. So let's do that, right? So let's first continuity. That's the first thing you do in calculus, continuity. We have a metric topology on this. We say that f a complex value function, is continuous at z0, z equals z0. Ready for the regular definition of continuity? If for every epsilon greater than 0, there's a delta such that z minus z0 less than delta implies what? Implies f of z minus f of z0 less than epsilon. Now, if you're looking at this, and if I replace all these z's over here with x's, x equals x0, f is continuous at x equals x0. If for every epsilon greater than 0, there's a delta such that what? Such that absolute value of x minus x0 less than delta implies absolute value of f of x minus f of x0 less than epsilon. It's the same definition. What's the only difference here? These are not absolute values. These are moduluses, right? That's a modulus. So it's a two-dimensional thing, right? And these are modulus, right? They're not what? They're not absolute values. They're moduli. So these things are two-dimensional limits. These are 2D real, of course, right? They're two real dimensional limits, right? And we know from Calc 3 that 2D real limits can be a little bit tricky to evaluate, right? That's what continuity means, okay? It's the same thing as for ordinary calculus. Great. All right, how do we do derivatives? Differentiation. Okay. So for example, if f of x plus iy was u of xy plus I v of xy, then what can I say? Then I can say two things. I can say partial f, partial x. The derivative of f with respect to the real part is going to be what? Is going to be partial u, partial x by linearity, plus I, partial v, partial x. And analogously, partial f, partial y is going to be what? Is going to be partial u, partial y, plus I, partial v, partial y. If the functions u and v are differentiable, then I can write down these expressions over here. So in other words, you just do ordinary calculus by linearity, right? All right, excellent. And so now what can I do? I can do integrals of these things over curves, for example. So how do I integrate? Now, of course, when you're integrating a function of two variables, you can think of this as, I can either think of this as a vector field and try to dot this with some differential, or I can think of these things basically just as integrals over curves, right? So for example, if I wanted to integrate, what would integration look like? Integration over a curve. And we're going to study this in depth too, right? So what I wanted to do, for example, if, for example, I looked at a curve over here in the complex plane. So if z, which is x plus iy, was z of t, which is x of t plus iy of t, give you a curve in the complex plane, then how would you integrate, for example, over a curve c of f of z, right, like this, with respect to a curve, right, with some differential over here, let's just say ds, right? That would just be the integral over c of u ds plus the integral over c of v ds. In other words, to do differentiation and integration of these complex valued functions, you're just going to appeal to the linearity of these functions, the linearity of differentiation and integration over this complex structure over here. Excellent. Now, of course, what we're going to see in further videos is these are just x and y derivatives, and these are just ordinary arc length contours. How can I write down different forms of integration and different forms of differentiation using Cauchy-Riemann, doing bar derivatives, different sorts of things like this? But as it stands, what we're going to do is we're going to use these formal algebraic computations. So these are, at least at this point, these are just the formal calculus rules. These are the formal calculus rules. In other words, I've used the same definition of continuity. I've used the same linearity properties. This is, of course, just the linearity of the derivative. Linearity of d by dx, d by dy, and the integral over here, right? If I use the linearity of those three things, then I'm really just extending the definitions from the real case to the complex case, using the fact that I know that a sequence of complex numbers converges if and only if the real and imaginary parts converge. So I'm really intrinsically using that fact that the real and imaginary parts of a sequence of complex numbers need to converge for the sequence of complex numbers to converge, which will allow me to take all of these ideas of continuity, differentiation, integration, which are all what? A limit, a limit, a limit, and translate them to the complex plane using that very elementary idea that a complex number sequence converges if and only if its real and imaginary parts converge. So now I'm able to basically extend the calculus from ordinary real analysis to complex analysis, which will give us a lot of leverage in further calculations. Thank you very much.